Neptune was supposed to be quiet, a distant frozen giant drifting in darkness, barely changing, barely moving. But when the James Webb Space Telescope turned its mirrors toward it, everything we thought we knew started to fall apart. Sudden temperature drops, mysterious bright patches glowing where auroras shouldn't exist, and a ring system lighting up like a cosmic warning. Something is happening on Neptune, and it's nothing like what scientists predicted. For most of human history, Neptune wasn't just unseen. It was unimaginable. You can look up at the night sky and spot 5 planets with nothing but your own eyes. Mercury, Venus, Mars, Jupiter, and Saturn all reveal themselves as bright, wandering stars if you know where to look. Under perfect conditions, even Uranus might give you the faintest ghost-like glimmer. But Neptune hides. It sits so far from the sun, so dim, so distant, that no human being had ever laid eyes on it before it was discovered. At an average distance of 30 astronomical units, roughly 4.5 billion kilometers, it is the true outer sentinel of our solar system, the last of the 8 planets, the cold frontier, and, strangely, the only planet we found using math. In the early 1800s, astronomers were closely tracking Uranus, a world that had only recently joined the planetary family. But something wasn't matching the predictions. Uranus kept drifting away from where Newton's laws said it should be. Tiny discrepancies, small deviations, but they were consistent, persistent, and impossible to ignore. Some blame the data, others blame the telescopes. But one mathematician, Urbain Le Verrier, believed the problem wasn't Uranus at all, but something pulling on it. With nothing but equations, he reverse-engineered the orbit of an unseen world. He calculated its position precisely, predicting where it had to be for the numbers to finally make sense. He didn't know its color, he didn't know its size. All he knew was that it existed. And on the very night his calculations reached Berlin, astronomer Johann Galle pointed his telescope exactly where the math said to look, and Neptune appeared, a planet discovered without ever being seen first. No other world in the solar system shares that story. But what followed was almost nothing. No wave of new missions, no detailed studies, no sudden obsession. Neptune became a footnote, a verified dot on the edge of the solar system. Too dim to follow easily, too distant to captivate the way Saturn's rings or Jupiter's storms did. Its discovery was revolutionary, but the planet itself remained ignored for over a century. Even its largest moon, Triton, discovered only days later, didn't change the tide. Neptune faded into the background, a wandering shadow locked in the outer dark. And in all this time, humanity has sent a spacecraft to Neptune only once. It wasn't even designed for Neptune. It was just a stop on Voyager 2's grand tour, a single high-speed flyby in 1989. No orbiting, no slowing down. Just one chance to see the planet before the spacecraft disappeared into interstellar space forever. Yet, in that single pass, Voyager revealed a world far stranger than anyone expected. A world that shouldn't behave the way it does. A world filled with storms, winds, heat, movement. In a place where almost no sunlight reaches. A world we barely know. And now, thanks to James Webb, everything we thought was true is starting to shift again. When Voyager 2 approached Neptune in 1989, no one expected fireworks. No one expected chaos. No one expected the most violent winds in the entire solar system waiting in the darkness. Neptune was supposed to be calm, a frigid, sluggish ice giant drifting more than 4.5 billion kilometers from the sun. With so little sunlight reaching it, scientists assumed its atmosphere would be quiet, frozen, and mostly uneventful. But as Voyager drew closer, the data told a completely different story. Neptune wasn't a sleeping giant. It was alive. Voyager's flyby brought the spacecraft just 5,000 kilometers above Neptune's cloud tops, closer than it passed by any other planet. And in that brief encounter, it collected nearly everything we still know about Neptune today. The first shock came from its winds. Supersonic gales roaring faster than 2,000 kilometers per hour, stronger than anything on Jupiter, Saturn, or even Earth during its most violent storms. It made no sense. Not at that distance, not with that little solar energy. Where was Neptune getting the power to fuel such atmospheric madness? Even now, we don't fully know. And then came the Great Dark Spot, Neptune's answer to Jupiter's Great Red Spot, a colossal swirling storm almost the size of Earth, churning near the equator and spinning in the opposite direction of the planet's rotation. But unlike Jupiter's centuries-old behemoth, Neptune's storms don't stay. They appear, drift, transform, and then vanish, as if the atmosphere itself is constantly rewriting its own rules. When Hubble looked again a few years later, the Great Dark Spot had already disappeared. Voyager also uncovered something else: Neptune's rings. Not beautiful and grand like Saturn's, but faint, patchy, incomplete. Some sections bright, others almost invisible. These ring arcs behaved in a way no ring system should. They should have spread out into a full circle long ago. But something, or someone, was holding them together. Even now, the exact mechanism remains a puzzle. And then there were the moons. Voyager discovered 6 new ones, all small, irregular, and tucked in close to Neptune's chaotic gravity. But the most remarkable was Triton, its largest moon, a world so strange it deserves its own documentary. Triton orbits Neptune the wrong way against the planet's rotation, suggesting it was captured from somewhere else entirely. And on its surface, Voyager detected geysers erupting nitrogen into the thin atmosphere, an active alien world further complicating Neptune's story. Voyager also revealed a magnetic field that defied logic. It wasn't aligned with Neptune's rotation axis. It wasn't centered. It was tilted, offset, and chaotic. Very similar to Uranus. That hinted at something deep inside Neptune, something unusual about its internal structure, something other planets didn't share. Maybe Neptune's magnetic field is generated unusually high in its layers. Or maybe the planet is hiding an interior far more complex than scientists realized. But Voyager's time was limited. One planet, one pass, one chance. And then it was gone, speeding toward interstellar space, leaving Neptune unexplored for the next 35 years. Everything after that came from telescopes millions or billions of kilometers away. Hubble became our primary eye on Neptune, revealing that the storms didn't stop after Voyager. New dark spots appeared in 1994, 2015, 2018, and 2020. Bright methane clouds formed and dissipated unpredictably. Temperature patterns shifted dramatically, with the stratosphere cooling by nearly 8 degrees in just 15 years. A swing no model could explain. Hubble showed us chaos. Neptune wasn't still. It wasn't stable. It wasn't behaving the way an ice giant should. And by the time the James Webb Space Telescope turned toward it, the planet had already become a mystery desperate for a second look. James Webb would do more than confirm those mysteries. It would expose new ones. Before James Webb ever looked toward Neptune, another telescope had already been quietly watching it for decades. Hubble became the planet's long-distance guardian, tracking its storms, its temperatures, and its shifting atmosphere from more than 4 billion kilometers away. If Voyager gave us the first close-up snapshot, Hubble offered the time-lapse, a slow, continuous record of a world that refused to sit still. One of the earliest surprises came in 1994, when Hubble detected a brand new dark vortex in Neptune's northern hemisphere. This alone proved that the Great Dark Spot wasn't a one-time phenomenon. Neptune was still generating storms on its own, massive systems forming and fading like cosmic hurricanes. And they weren't predictable. Some storms drifted toward the equator and vanished. Others reversed direction entirely, moving back toward the pole as if something deep within the atmosphere was steering them. Alongside these storms, Hubble observed bright methane clouds, thin, high-altitude formations that clustered around the vortices. Sometimes they appeared before a storm formed. Other times they wrapped around the edges like glowing outlines. But they never stayed the same. They changed shape, brightness, and position within days, telling scientists that Neptune's atmosphere was being stirred from below by processes we still don't understand. Then came one of Hubble's most intriguing discoveries. In 2013, a tiny moon, only 34 kilometers wide, revealed itself, tucked just outside Neptune's ring system. Named Hippocamp, it had been completely missed by Voyager 2. If a moon that small escaped detection, how much more could still be hiding in Neptune's shadows? Hubble also refined the orbits of Neptune's other inner moons, showing that some, like Naiad and Thalassa, weave around each other in an intricate, synchronized dance to avoid collision. But perhaps the most puzzling information came from Hubble's temperature readings. Between 2003 and 2018, Neptune's stratosphere cooled by almost 8 degrees Celsius, an enormous drop for a planet whose seasons last 40 years each. Then, around 2018, the South Pole began warming rapidly. These sudden swings didn't fit seasonal models. They were too extreme, too fast, and too inconsistent. Something else was happening inside Neptune's atmosphere, something our telescopes could measure, but not explain. Hubble didn't solve Neptune's mysteries. It amplified them. It revealed a planet with a volatile climate, ever-shifting storms, unstable temperatures, and moons that behave in ways no one predicted. It set the stage for what came next. Because when James Webb finally turned its massive mirrors toward Neptune, the picture became even stranger. When the James Webb Space Telescope first pointed toward Neptune in 2022, astronomers expected clarity, detail, precision, but they did not expect transformation. Webb didn't just give us a sharper image, it gave us a new planet, a Neptune no one had ever truly seen. Gone was the deep sapphire blue we were used to from Voyager and Hubble. Infrared light stripped away the color we knew and exposed something pale, ghostly, almost transparent. Through Webb's eyes, Neptune became a world shaped not by hue, but by heat. A world defined by structure, by altitude, by layers hidden beneath decades of haze. The 2022 Webb image stunned scientists when it revealed Neptune's rings with clarity unseen since Voyager's flyby. Not faint suggestions, not incomplete arcs, but crisp, luminous structures glowing in infrared light. The rings weren't uniform, just as Voyager had hinted. Some sections gleamed brightly, while others faded almost to nothing, creating a fragmented halo around the planet. Their odd, uneven appearance revived questions about what holds them together and why they behave unlike any other rings in the solar system. But Neptune's rings were only the beginning. Webb also unveiled multiple layers of methane ice clouds stacked high above the atmosphere, bright, razor-sharp formations, each marking regions where the atmosphere was rising, cooling, and condensing. These clouds revealed patterns of movement no telescope had seen before. Not random, not uniform, but rhythmic, almost like Neptune's atmosphere was pulsing. Still, this was only the first look. The real shock came with Webb's expanded 2025 observations. In the new images, Neptune wasn't just visible, it was glowing. Webb detected bright infrared patches scattered across mid-latitudes, lighting up the atmosphere in regions where auroras shouldn't exist. On Earth, Jupiter and Saturn, auroras cluster around the poles, but Neptune is different. Its magnetic field is tilted by nearly 47 degrees, offset from the planet's center in a way that bends charged particles into strange trajectories. Webb's images captured those particles slamming into the upper atmosphere, igniting patches of heat and light far from the poles. These glowing regions weren't faint details. They were bold, vivid, unmistakable, and they were accompanied by strong spectral signals of H3+, a molecule created when energetic particles collide with gas in the upper atmosphere. H3+ is the fingerprint of auroras, and Webb detected it across latitudes where auroral activity had never been seen before. For the first time, scientists could trace Neptune's magnetic chaos as it was happening. But Webb didn't stop at auroras. It also recorded temperature anomalies, revealing dramatic cooling in some regions and unexpected warming in others. Effects that didn't match seasonal patterns and didn't align with Hubble's earlier data. Neptune's stratosphere appeared to be behaving unpredictably, almost erratically, as if some deeper internal process were interacting with solar particles in ways we still don't understand. Then there were the storms. Webb saw bright methane clouds clustering in new patterns, forming and dispersing within days, echoing the chaotic behavior Hubble had recorded over decades. But now, for the first time, scientists could see beneath the haze. Webb's infrared vision penetrated deep enough to provide clues about how Neptune's storms might be connected to the internal heat the planet emits. Heat more than twice what it receives from the sun. The 2025 data also exposed subtle changes in Neptune's ring arcs, hinting at gravitational interactions that may involve small moons or clumps of unseen material. Webb's sensitivity detected shifts too small for Hubble to register, suggesting that Neptune's intricate ring system might be evolving in real time. And perhaps the most profound result wasn't an image, it was a question. If this is how Neptune behaves now, in just a handful of observations, what would we find if we actually went back? Neptune is the most common type of planet in our galaxy. Ice giants like Neptune and Uranus dominate the exoplanet catalog. Yet we've spent more time studying Mars, Jupiter, Saturn, Pluto, even moons like Titan, than we have on the fourth largest planet in our own solar system. James Webb didn't solve Neptune. It exposed how little we know. It showed a world powered by hidden heat, wrapped in unpredictable storms, glowing with auroras in places they shouldn't exist, surrounded by rings that defy gravity, and changing faster than any model can explain. And with every new observation, the truth becomes clearer. Neptune isn't just another planet. Neptune is a warning that the outer solar system is far stranger and far more active than we ever imagined. James Webb's revelations didn't just deepen Neptune's mystery, they reignited an old question humanity has avoided for decades. Why haven't we gone back? We've orbited Jupiter and Saturn. We've mapped Mars in higher resolution than Earth's oceans. We flew past Pluto and turned it from a blurry dot into a world of mountains and frozen seas. We even dropped a probe onto Titan, a moon so distant it receives only 1% of Earth's sunlight. But Neptune, Neptune has been left alone in the dark since 1989. The brief moment Voyager 2 passed by at high speed, captured everything it could, and vanished into interstellar space. One visit, one chance, one snapshot. And everything we've learned since then, every storm, every temperature shift, every vanishing vortex, every unexplained ring arc, has come from telescopes billions of kilometers away. It's not enough. If we want answers, we need to return. Not with another flyby, but with an orbiter, a spacecraft designed to stay. An orbiter could watch Neptune's storms form and dissolve in real time. It could map how heat moves through the layers and finally explain why the planet radiates twice the energy it receives. It could measure the magnetic field up close and understand why it's so tilted, so offset, so unstable. It could fly through the ring system and reveal whether the arcs are held together by unseen moons or something more unusual. And maybe, just maybe, it could drop a probe into the atmosphere to measure pressure, chemistry, turbulence, everything that shapes Neptune's violent climate. Beneath Neptune's clouds lies a world of ices, methane, ammonia, and water, compressed into exotic forms under unimaginable pressure. Scientists believe methane deep inside could break apart, forming diamond hail raining through a superheated ocean of carbon. If true, Neptune may be home to physics no other planet shares, physics that could rewrite what we think we know about planetary interiors. And it matters for more than Neptune itself. The majority of exoplanets we've discovered are Neptune-sized. If we don't understand the ice giants in our own backyard, how can we hope to understand the thousands orbiting distant stars? NASA scientists have proposed missions like Neptune Odyssey, a flagship concept that would orbit the planet for years, investigating everything from atmospheric chemistry to internal structure. But proposals aren't missions. They need funding, approval, and decades to build. Meanwhile, China has announced plans for a possible Neptune probe around 2033, one that could fly past or even enter orbit, offering humanity's first return to the ice giant in nearly half a century. If that mission succeeds, the first new close-up images of Neptune may come from halfway across the world. For now, all we have is the sky. Webb will keep watching. Hubble will keep tracking. But from this distance, we're only seeing fragments, hints of a world that refuses to reveal itself fully. Neptune is calling. It's time we answered. If this journey into Neptune's mysteries opened your eyes to how strange our solar system truly is, make sure to like this video. It helps the channel more than you think. And tell me in the comments, should Neptune be our next big mission? I read every single reply. Don't forget to subscribe for more mind-bending discoveries from across the cosmos. This is Stellar Path, and we're just getting started.